明白了吗？喂喂。对，送了。听到了吗？没有啊。喂喂。喂喂喂。这个应该，
这个是第一个人的。
这个就是说。说话了吗？老王，你回来。不行，没有信号了他。啊，你那没有网。
and that's the laser pointer.
This is the laser pointer.
Yeah. You can shooting this way. Yeah, that's the way. Yeah.
It works.
This is the that's forward. This is back. Where's the back? Okay, this is back. And this
Can we try it?
Yes.
Yeah.
They will change. So just a second.
Yeah,
I think we need to share the this one. Otherwise,
Hi. You see so many people.
这个 Zoom 好像不能分享啊。
可以的。
要先退出来。
让他试一下。好，那你们在这搞啊。
这有什么问题？
它现在就是显示的小。
厕所在哪？厕所在哪？
在外面，在外面。
你们能领一下吗？
点不出来了。在这个，但是这个是最小化的，我给您重新登一下吧。它这个最小化了。
我先把他电脑换过来。
快去！喂，你说。对，我这边说话能听到了是吧？不到。
喂。
来看，让我们的音乐。
各位老师、各位同学，大家晚上好！请没有找到座位的同学尽快入座。2楼还有很多位置，好吗？我们动作快一点。2分钟之后，我们将开始今天晚上的报告。请没有找到位置的同学尽快上2楼，到2楼入座。2楼和3楼都可以坐。我们的报告将在2分钟之后开始。
这里还有个主持，现在就2个下去是吧？全部来下去。
行，我觉得我们应该大家都做好了啊。All right. Good evening, ladies and gentlemen, and esteemed scholars. I'm Qingmin Nu, the president of Hainan University. Tonight, we're gathered in Haikou, the coconut city, for the public lectures by Nobel Laureates, hosted by IUPAP, the International Union of Pure and Applied Physics. This year marks IUPAP's 100th anniversary, and it is an honor to have their General Assembly in China for the first time. As part of this amazing event, IUPAP has organized a series of exciting activities following tradition. Tonight's public lectures by the Nobel Laureates are definitely one of the highlights that gave us a rare chance to learn. We are privileged to welcome 3 distinguished Nobel Laureates. Professor Barry Clark Barish, who won the 2017 Nobel Prize in Physics. Professor Takaki Kajita, winner of the 215 Nobel Prize in Physics. And Professor Samuel Ting, winner of the 1976 Nobel Prize in Physics. On behalf of Hainan University, I want to extend my warmest welcome and sincere greetings to our guests from home and abroad. Now, it is my pleasure to introduce the president of IUPAP, Professor Michel Sparrow, who will chair the lecture sessions. Professor Michel, please.
Thank you, Mr. Chancellor, for your kind words. Thanks to the Chinese Physics Society to co-organize with IUPAP this series of public lectures by Nobel Laureates, 3 public lectures. So this is a special evening session jointly organized by IUPAP and CPS. A word on IUPAP, because maybe you don't know much what is IUPAP. The name was mentioned by the Chancellor, so it is the International Union of Pure and Applied Physics. It is the only global organization for physics. Its goal, first goal, is to contribute with physics to a better understanding between people over the world. It is also to stimulate the worldwide participation to physics and to stimulate the collaboration worldwide also in physics. It is also to foster the applications of physics which could be of concern, which could contribute to solve problems of concern to humanity. So this means contributing to equitable development and a healthy planet. I don't want to say much. I hope you got the message. And I want to introduce now the first speaker, Professor Barry Barish, California Institute of Technology in the US. Professor Barry Barish was awarded the 2017 Nobel Prize in Physics for his work on the Laser Interferometer Gravitational Wave Observatory, LIGO, and the first detection of gravitational waves. Professor Barry Barish, please.
So, first, I'm impressed by the audience. You're gonna hear lectures on very abstract forefront fields of science. And I'm impressed that you're willing to sit for 3 hours for 3 of us to talk. I'm gonna start from something that you know, which is gravity, and move on very quickly to a new topic, a subtopic of gravity, gravitational waves. I'll tell you how we got there. And then I'll talk about how we have discovered gravitational waves. And then I'll talk about how this is opening up a whole new science that we're just barely beginning to exploit. So let's begin. The picture here is a picture of a cartoon that kind of shows the elements. What's shown in the middle are 2 black marks. Those represent black holes, something very, very modern, which I'll describe. They're actually colliding with each other and emitting what we call gravitational waves, which I'll explain. And the other part of the cartoon is just a picture of the kind of way that we go about detecting them, which I'll describe to you as well. So let's begin in a very familiar way with Newton. Newton is the most important physicist probably of all time. He certainly wrote the most long-lasting and important theory, which is the theory of gravity. And he gave us a theory of gravity in 1687, after working for almost a half a century on the problem. To do it, he had to develop the calculus that was needed to do the problem and to convince himself and others that he really solved the problem. Physically, the problem was whether this inverse square law, which is here, that the force of gravity goes inversely as a square of how far apart objects are that are attracting each other, implies that you get elliptical orbits or planets going around the sun. In order to prove that, he had to use calculus that he had to develop, which he did at home because he was stuck at home with something worse in COVID when they had the plague in the 1680s. And he solved the problem mathematically then and proved that you could get elliptical orbits from this equation. But that didn't mean that it has the first word that he used. When he wrote the book, the famous book Principia, he called it the universal gravity, or universal theory of gravity. And to prove to himself that that was true, he had to find some other application of his formula for gravity. And that he did by predicting the orbit of a comet that came into our system, Halley's Comet. And that gave him the confidence to publish the book. That stood for longer than almost any physics theories before Einstein came along. And the first lesson is that all theories of physics, even the best ones like this, are approximations to nature. We find that we need to extend them, not necessarily reject them, but extend them to take care of phenomena that we learn are not really covered by, for example, in this case, Newton's theory. So I'll tell you why and how, but Einstein then developed his own theory of gravity in the early 1900s. I'm not going to explain this formula, but it's the more or less equivalent formula from general relativity, his theory, to Newton's theory. And his theory is based on space and time, not the attraction of a force that pulls the apple from the tree, for example. So let's look at this a little bit. His theory, Newton's theory, lasted, as you saw, for more than 200 years. In the more than 200 years, there was only one observation that implied maybe his theory wasn't able to completely describe nature. There were times before that where people questioned it, but it always proved to be true. And the problem that existed, and the only problem with Newton's theory that existed when Einstein came in the early 1900s, was the orbit of Mercury around the sun. Mercury is our closest planet to the sun, and it has a very elliptical orbit. And each time it goes around, it's pulled by the moons and planets and everything in the solar system, and it comes back in a different place. You can calculate all that if you know all the objects. And when you calculate it, and this was done in the late 1800s, when you calculate it, you get a number, which I've written here, how much it moves forward the next time it comes around. And the observed amount was a little different than Newton had predicted, by about 10%. And that was the only place where Newton's theory didn't explain nature when Einstein came around. In fact, people had physical explanations for this, which was mostly that there was an unseen body that was between Mercury and the sun, which turned out to not be true. Newton's theory doesn't quite give the right answer, but Einstein's does, as I'll describe. So Einstein's theory is completely different conceptually. It's based on the fact that gravity itself affects space and time around it. So it's built as the actual structure of space and time. And the space and time, when it's disturbed, then tells any object that has mass how to move. So the space-time gets affected by the presence of masses, and space-time being affected then affects how other masses are moved. That may sound a little strange, but when we look at this picture here, I redraw it with the Earth with a distorted system because the Earth is sitting in that system. And you can imagine this like a trampoline on a beach. If there's another object there, like the moon, it's then attracted to the Earth just because it rolls downhill, basically, or is trying to roll downhill. And that is the attraction that you get due to the curvature of space-time, which is Einstein's picture. While that implies then anything that's near a body gets affected by the curvature of space and time. So Einstein predicted something new. And that's the second thing that has to happen in a new theory. First, he made some corrections to the theory that Newton had. And then secondly, he predicted something new. In this case, what he predicted as new seemed very, very odd. And that is that light itself will not go in a straight line if it's in the presence of a massive object, but will be bent by the fact that the curvature of space and time have been affected near that object. And the way to test that, he also proposed, which is to look at stars just as they're moving behind the sun at the time of a full eclipse. And that was done by Sir Arthur Eddington in 1919. And that was what made people believe that Einstein's theory was indeed correct. As is true for most theories that we develop when we develop a new theory in physics, is that often it becomes then useful as a help in understanding other phenomena. And now the bending of light around an object is a very common tool used by astronomers in order to analyze objects that they can't image in the telescopes themselves. So I show, So I show two examples here. On the right, which is looking at the light when there's objects in the sky. The one that's most famous is the one on the bottom called the Einstein cross, which you can almost see with your naked eye. And it has this pattern due to a cluster that's behind it, and then imaged by the fact that it again is bent as it goes by the object in the middle. There actually was a conceptual problem with Newton's theory that he recognized. And that was in his text, in the book that he wrote. He kind of puzzled over the fact that his theory has, in his words, instantaneous action at a distance. That is, when the apple falls, you detect the apple immediately in his theory. But if you can imagine that the sun were to disappear right now, we know that it would take 8 minutes before we would know anything, because that's how long it takes the signal, in this case light, to travel from the sun to us. So in most cases, it's logical that it takes some time for a signal to propagate from an action to an observer, which is us. In the case of electromagnetism, it's the speed of light. For gravity, it's also going to be the speed of light, as I'll show you in a few minutes. But this was a conceptual problem that was fixed also by by Einstein's new theory of gravity. I'm going to leave that and talk then about the new physics that he proposed. 1 year after he produced his new theory of gravity in 1915, he noticed that if he wrote down the equations of gravity in a certain way, using his theory, although the letters were different, it looked like the equations of electricity and magnetism. He didn't derive anything. He just, from that, made the leap and the conjecture that since electricity and magnetism has waves, electromagnetic waves, light waves, microwaves, and so forth, that since the equations looked alike, then from his point of view, gravity must also have waves. So in this paper in 1916, he proposed that there were gravitational waves. He also predicted that they would be impossible to detect. And that is because he could recognize that they were extremely small. I'll explain why in a second. But he couldn't project that 100 years later we would have the kinds of instruments, advanced lasers and so forth, that has enabled us to actually measure these very small disturbances. Gravitational waves themselves are kind of a natural consequence then of his theory and special relativity, and that is that that also has finite time for information to travel. So the gravitational waves travel at the same speed in this theory. And basically they come, if there's accelerations of masses that will produce the gravitational waves. A good example of that is a barbell that then you spin around, and that's like two black holes going around each other. The effect is so small, and our ability to detect such small things isn't good enough yet, that we need to find something like two black holes to give us a big enough signal. We couldn't do it in the laboratory. When I learned physics, one of the first lessons that I learned in the laboratory is that as a physicist, if you want to get the right answer, you should control everything, control all the variables. So when I started on this bothered me a lot that we couldn't, in this case, control all the variables. Instead, we had to rely on nature to give us produce gravitational waves that we could detect. On the other hand, even though that bothered me because I had learned that I should control everything, that gave us the opportunity, once we detected them, to understand phenomena like black holes merging. So it works both ways. So let me show you what so gravitational waves produced in something like these two black holes going around each other. They're losing energy to gravitational waves and slowly spiraling in and colliding. So while they're doing that, they're emitting gravitational waves. They go through space as ripples in space-time itself at the speed of light. And those basically cause space and time to stretch and squash together as they travel through space. The amplitude of these waves for something like we observe is very small. I show here a number, and that number represents kind of how big of an effect it is. It's a lot of zeros and a 1, 10 to the minus 21. So that's the size effect we had to try to measure. So if we try to measure something, but that's this little h, something over some detector that's a certain size, then the change in length of the detector is that little h times L. If I multiply those together, we can see what the effect would be. What I'll look at is a circle. So imagine a circle, and on the circle we place free masses around the circle. They're free to move if something pushes them or if they're not. And technical problems. And so the idea is that when a gravitational wave comes through this circle, it'll change the shape. It'll first make it elliptical a little bit vertically, and then elliptical horizontally with the frequency of at the frequency of the gravitational waves. So if I put in numbers, it's stuck. Oh, it's okay now. Oh, no. So if I put in numbers, then I've done it here for you. The change in length in that circle is a very tiny number, that 10 to the minus 21. So if my little circle of masses is a meter, then the amount that it'll change is 1 part in 10 to the 21 or 10 to the minus 21 meters. That's an incredibly small number. In order to make it a little bit bigger for us to be able to detect it, our little circle is actually a kilometer instead of a meter, or several kilometers in the detector that I'll show you. So the idea then is to take something that can measure simultaneously the length vertically versus the length horizontally. And there's a very good instrument to do that called an interferometer, which I show here, where you send light and then divide it in the two directions, let it go down a kilometer or several kilometers and come back. If there's no gravitational wave, they'll come back and exactly cancel each other. And that's what's shown now. But if the arms become slightly different in length, like we're trying to measure, then they won't come back at exactly the same time, and we can see a signal in our device. And so that's the scheme. That's got a word. It's called interferometry. So that's the idea of an interferometer. And the rest is just making it work very well. So this picture that I'm showing, which is basically a gravitational wave at a couple times a second, is measuring this 10 to the minus 21, or measuring something like a few 10 to the minus 18 meters, because it's 4 meters on a side. And that requires us to actually measure a change of length caused by the wavelength of the light itself, compared to the wavelength of the light itself, to 1 part in 10 to the 12th. That's a very accurate measurement of the light itself, that it moved by just 1 part in 10 to the 12th of the length of a laser that has a frequency just out of the visible light. And technically, for other devices, and I'll just pick one, we have to also get rid of the backgrounds at about the similar level, 1 part in 10 to the 12th. The one I use here is that our apparatus is sitting on the Earth, and we have to isolate it from the vibrations of the Earth to 1 part in 10 to the 12th. I'll just give you a sense of how we do that. So that's the problem. Once we can do that, if there are merging black holes, we can detect them. So we were approved to build such a device in 1994 by the National Science Foundation in the US. And we have built 2 detectors, one in the state of Washington in the northwest corner of the US, and the other one in the state of Louisiana, a small town called Livingston, Louisiana. And the distance between the two is about 3,000 kilometers. What that means is if there's a gravitational wave and it's coming up from the bottom like this, it will hit this detector 10 milliseconds before this one, or coming down, it'll be 10 milliseconds before the other one. But that means any configuration, they'll be within 10 milliseconds of each other, and that is what we look for a signal. And then we look when they shouldn't be in coincidence to test what kind of just random backgrounds from instrumental effects we get otherwise. So that's the idea. We have 2 detectors. This is a picture of them. They're absolutely identical. And when we change a little resistor in one detector, we immediately change it in the other one to keep them identical. They look very different here because they're on very different physical places. The one in Washington is on high desert, and so that's very stable. High desert, very dry. In Louisiana, it's in a pine forest that's used to harvest trees to make paper. And we just have a little piece of land that we bought in this pine forest. So this is the interferometer, and I'll just give you an indication of the kinds of things that make it difficult to make such an accurate instrument. First, the laser, first I show the fact that if you send light to 4 kilometers, it's going to scatter on the air that's in the 4 kilometers. So it has to be at high vacuum to eliminate as much as possible any scattering of light. Second thing is the laser itself. We think of a laser as very, very accurate, very precise, but our lasers are much better than any that you can find commercially or in any laboratory, where they've been stabilized in the wavelength that they shine the light in the amplitude fluctuations and so forth, and pointing with very sophisticated electronics. Then the mirrors, where the beam goes all the way down and hits a mirror, those are shaken by the ground, just the fact that they're sitting on the ground. And that's when I said we have to isolate those from the ground to 1 part in 10 to the 12th. Believe it or not, the ground is really shaking below you. This one is the most sophisticated. And no, this is not, the next one is. This is basically the fact that any mirror, which is something you look at and is shining, is made out of material, and the atoms are always moving around in the material, and that causes something we give a name to. We call it Brownian noise, which you can calculate. And so we try to pick a very pure material for the mirror's made out of, so reduce that as much as possible. Then this one is the most sophisticated one. It's what we call quantum noise. In words, what it is the fact that in order to keep getting better and better measurements, you increase the amount of light you use, or how many photons you use. The more photons, the better. You have a better measurement. But if you use more photons, you put more pressure on the mirrors. And at the level of atomic and quantum physics, it moves the mirrors a little bit. And so that uncertainty produces another limitation in the, which we call thermal noise in the thing. So I'm not going to go through it, but this is just to illustrate that starting from the simplest concept of an interferometer, we've done 20 years of work to make it very, very sophisticated in order to do the elimination or the measurement of a shift in the wave of the light itself to 1 part in 10 to the 12th of the frequency of the wavelength of the light itself. And to get rid of the ground, as an illustration, we use 2 techniques. One is shock absorbers, like you have in your car, but the most sophisticated shock absorbers you can imagine. Thank you. And there's 4 layers of those. So like your car keeps you from kind of feeling every bump, we do it with much better shock absorbers. And then what isn't gotten rid of in the first layer is taken care of in the second, or the third and the fourth. That isn't good enough to get to 10 to the 12th. So we do one more thing, which is very sophisticated and took us a long time to develop, which is to actively detect what motion is left and to push back against it. So we basically have seismometers that are buried inside, measure any motion, and we push back against it. And with that combination, we got to 10 to the 12th. All of that got us to where we built a detector that we turned on and saw this almost the first few days that we turned the instrument on. What's shown in the left, you'll notice, has the 10 to the minus 21. So what you see on the right is a scale that goes for 0.2 of 1 second. And in that 0.2 of 1 second, you see a warm wave that gets bigger and bigger and then comes together. So it gets bigger and bigger along here, comes together, and then gets small again. That was interpreted by us and theoretically as the merger and collision of 2 black holes that had been going around each other and finally came together. A little bit better to see is this plot here, which is the same data. But if you look at the second line, instead of the first line is the data, just like I show on the left. The second one is actually Einstein's theory, using Einstein's theory to calculate what it would look like for 2 black holes. And you can see it's smoother because it doesn't have experimental noise, but they look almost alike. And for me personally, when we took this data, what convinced me that it looked like it was right, except for things that we couldn't tell by this, is the third frame, which just shows random shaking. As an experimentalist, if there's something else besides what we've done, it would show some sort of pattern of something other than just random noise. So that was this is the figure from our publication, and that was the discovery of gravitational waves. So now we'll move on. That's been done. That was a big deal. That's what I got my award for. But now we're moving on, and so I'm going to talk a little bit about moving on. First, let me say a couple more things about this event. If you look only at the numbers on the left, you notice that it says there's a primary black hole mass of 36 with an error on it, plus 5 minus 4, times the mass of our sun. That's what that little circle means. And the second line shows the second black hole. These are the two that collided, of 29 plus 4 minus 4 times the mass of our sun. We know those numbers, or measured those numbers, those oscillations that went back and forth. And from the actual frequency that it ended with, we can tell what the masses were of the two objects. But we all know how to add. If you add the first number and the second number, you get 65. So you'll notice the third number, which is the final black hole, says 62. The difference between 65 and 62 is that the equivalent of 3 solar masses, the mass of our sun, were carried away in the form of gravitational waves. So when this collision happened, in some sense, it was the brightest object in the sky for that 0.2 of a second. So we're doing more, it's a continuing story, and I'm going to not talk about the technology, but maybe what we can do with physics in a few minutes. But for example, in the case where I said quantum physics came in, and that is the pressure on the mirrors, we have techniques that can use quantum physics to reduce that. And that's shown here, where it says no squeezing. It's what we did in the data that you saw. And squeezing is the latest data where we actually have reduced the background. That enables us to see further out into the sky and more events. I'm not going to talk any more about technology particularly, but more about the science that we can do. But we've gone through those kind of improvements. That's the one being instituted right now. But you'll see here on the left, 01, 02, 03, 04. It's calendar time on the bottom, days, and you can see the slopes change. The first one was our detector, the first 100 or 200 days at a low slope. Then it got steeper and steeper, and we're now in the fourth one. That brings you up to date. So each time we turn off the detector, we make it better. We can see further out. That very rapidly brings us more data because we see the whole sky, and it goes as the cube because that's what the volume of the universe goes as. So we now have seen roughly 250 to 300 examples of these kind of gravitational waves, and we're detecting one every day or two at present. So with that, not talking about it in detail, we've done a lot of science already, and we're looking forward to the first. So if we look here, on the top left is the most accurate tests that have been done of general relativity. And I'm not going to explain the graph in detail, but that's from our publication. So far, we've seen no deviations from Einstein's theory itself. The one on the top right is the whole compendium of the black holes mergers that we've seen so far. And as we increase how far we can look out in the universe, it won't be too long, maybe 4 or 5 years, we'll be able to see to the edge of the universe. When we can do that, we can tell when these black holes were born. Were they born primordially or at the beginning of the creation of the universe, or where along the way, for example? So that we're pursuing. On the bottom left is the puzzling events that we've seen already. So in the 200 and some, all are not explained. We're not announcing discoveries because it's too early, but they're not explained. And in this case, what I show you is that we know there are objects a little bigger than our sun that we call neutron stars. They're 1.4 times the mass of our sun. And then there's heavier objects, which we call black holes, but they can't be black if they're too light, so they can't be a black hole unless they're roughly, people think, 5 times the mass of our sun. We have events, this is just an example, that are in between those two. Are they measurement errors? Are they real? We don't know yet. So that's just an example. And in the bottom right, I'll concentrate on a little bit more, is what we feel is the most promising scientific field we have to look forward to, which is the combination of seeing phenomena in the universe that give gravitational waves and electromagnetic signals for astronomers. And this is data that I'll show you from our example of that. In order to combine gravitational waves and astronomy, we need 3 instruments. We have to triangulate. This is just a picture of triangulating. Just like a ship in the ocean, tell us where it is. If we look at the picture on the right here, this is kind of how well we could do with LIGO itself. It's basically just a stripe around the Earth, and so it's not well located. We can do a little bit better than that by some tricks, and so it doesn't go quite all the way around the Earth. But there's another gravitational wave detector, not as sensitive as LIGO, but this event was all the help we needed, and that enabled us to see this accurately where in the universe it came from. That came, as you can sometimes be lucky as a scientist, it came at a time when, let me skip this. This is just showing you the triangulation. It came soon after we could triangulate, and the graph on the left shows you what we observed. The top one and the second one and the third one are all satellite high-energy gamma ray observations, and they see some sort of a signal, noise, which you always see, and then a signal in here. And it was verified in several satellites. So that was a signal that was known by them to come from a neutron star system. And then our pointing was in the same region as theirs. This is the picture of theirs and ours, ours was actually a little better. And this is the signal for us, shown in a different way than I showed before, frequency this way and time that way. So as we change the time, the frequency gets higher and higher, and the signal's here. So you'll notice I've projected that up through these. And what we've seen then, very quickly, is a gravitational wave signal in the same place in the sky as 3 satellites, and within 1.5 seconds at the same time. It was quickly seen then, but that gave us enough confidence to alert the astronomical community to look at all their telescopes around the world. And there were actually 2,100 recorded observations of something in this signal by some sort of astronomical instrument. So that's the mobilization of everything, including even neutrino detectors. You're going to hear about those next, but they weren't quite sensitive enough to detect this. And fortunately for us, they were able, in the electromagnetic measurements, to actually see what galaxy it came from. So we could point to the same thing, same area, but they could tell us exactly what galaxy it came from, which told us how far away it was. And it was 150 million light years away. So if I go back to this picture here, within 1.5 seconds, we see a signal that came from the same source that is seen electromagnetically 150 million light years away. 150 million light years is 1.5 10 to the 15 seconds. So this picture itself tells you that light and gravitational waves travel at the same speed, which is what Einstein predicts, to 1 part in 10 to the 15, which is pretty impressive. So that's a preview of what we'll be able to do once we have more detectors that can help us do the astronomy. This is just the pictures of the different frequencies where the observation of that event was seen. Interestingly, what happens then, this is just, again, a confirmation of that. And I'll show you on the next slide something you're all pretty familiar with, which is the periodic table. From the time I was a student, like you, there was a puzzle about the Earth. And the puzzle was the following, that we know that the universe is made mostly out of hydrogen, helium, and beyond that, there's stars, and stars have all the elements up to higher elements, and stars burn slowly by the fusion process. The fusion process starts by burning the hydrogen and helium, and that's most of the lifetime of a star, like our sun. But eventually, when they burn up the hydrogen and helium, then they start burning up the heavier elements. When they burn up enough of them, the outward pressure from the burning, like the sun, it no longer can compensate gravity, and the star collapses, and you've probably heard that word. It's called a supernova. So that gets you up to iron. But it was a puzzle. Where did heavy elements, maybe our favorite ones like gold and platinum, come from in the Earth? And physicists always have to be able to explain everything. So there was basically a nuclear theory explanation that it was due to some obscure effect called the R process. Well, and it was actually happened from the burning of stars and the collapse of stars. Well, instead, it's now quickly believed that heavy elements, like our favorite ones, platinum and gold, actually came from this kind of process of the collision of 2 neutron stars like we just observed, but obviously at some earlier time before the Earth was formed. If you just take the observation that we made, the one that I just showed you, and go through the calculations of how much gold was produced in that collision itself, it's 100 Earth masses of gold. So that's pretty impressive. It's not what got gold in our Earth, it just happened, of course, but some event like that in the past may have done it. This is a good illustration of how often in science we discover things that are way afield from where our real first objective was, and we have to keep our eyes open and look at all the possible consequences of whatever we observe in nature. So I'm going to tell you now, there's a puzzle. I'm going to skip this because I'm running out of time. I'm going to talk a little bit about the future, and then I'll end. So we know how to make this detector better and better over the coming decades. We're making the ones that we have now better over this decade, and you'll see other things, a lot to look forward to over the next 5 to 10 years. Then on the Earth, we plan to, hope to, if we get funded, to build the next generation detectors, more sophisticated and larger. So there's a different idea for how to do that in Europe and in the US, and I just show them both here, but I won't take the time to explain. The main difference is that in Europe they have less land than we have in the US, and so they want to put the detector deep underground where it doesn't disturb things as much. And we, in the US, plan to put it out in the part of the US that isn't very populated. So this is just the concept, which I'll skip. It has beautiful, these are the best and most beautiful mirrors in the world. They'll be even better for this device. And the big problem that we have, which I'll come to, is how to build such a huge, high-quality vacuum system without spending too much money or breaking the bank. And so technically, we're doing a lot of work, especially with the CERN laboratory, who have different reasons for wanting to improve how to make high vacuum, trying to make a vacuum system that will be affordable. And it's the biggest kind of technical issue that we want to solve before we actually propose to move forward with that. We have another 5 years or so, so we have time to solve that. This is just an example that doing this kind of observation and comparing it with what's done on accelerators, what we do is try to simulate in the lab or have the same conditions in the laboratory as existed in the early universe. So what's shown on this one graph is what happens in these neutron star kind of collisions, which is our data from gravitational waves, and data that comes from very high energy accelerators shown on the left, and from what are called heavy ion colliders, where you collide not protons, but heavy ions, and they cover much of the region of temperature and density that existed in the very early universe. So since we can't go directly to the early universe, our way of doing it as scientists is to cover the same kind of conditions and try to make an interpretation of the observations that'll help us understand what happened in the early universe itself. For gravitational waves, we will do the same thing that has been done for electromagnetic waves, which is not limit ourselves to the frequency band that we study on the Earth, which is shown where it says LIGO here, but also lower frequencies. And there's a approved and funded and being built space mission in Europe called LISA, Laser Interferometer Space Antenna, in order to move to the lower frequencies. Yet at even lower frequency, it's possible to detect gravitational waves from known pulsars. These are the result of a collapse of a star making what's called a pulsar, a spinning neutron star that gives radio signals that we detect. So just like in electromagnetic interactions where we use radio waves, high energy gamma rays, which I showed you, visible light, and all of that to do astronomy, we will do the same kind of thing as we go forward with gravitational waves. That is, look at the whole wide frequency band. So this is just the orbit of the space mission, which is supposed to fly in about 2035. It's just how they'll mount it. And they've already done a mission to prove the technology itself, much like I showed you we have to do on our technologies. And that was very successful, so they know how to do that. And this is just a picture of how the pulsar timing using known objects that are good clocks in the universe will also change when curvature of space-time comes through, and the relative timing of these devices is a little bit different. There's already preliminary evidence that they may see gravitational waves. It's not at the level that we declare victory as scientists, but the shape shown in the dashed line is what we calculate for the kind of disturbance that would happen if a gravitational wave goes through at low frequencies to these relative pulsar timing, which is shown here. The data looks consistent with this, but this is not yet statistically significant, and it'll probably take another 5 to 10 years before it will be. So the last is that the best present probe we have to understand the early universe is to look at what's called the cosmic microwave background. And that's to look at the frequency of light, called the microwaves, that actually are in the whole sky, and they're very prevalent, to look at them in a way that gives us a picture of what the universe looked like 400,000 years after the Big Bang. And it's 400,000 years because before that, the universe was so dense that it was opaque to these microwaves. But now they can measure those. In that, there can be the imprint of the fact that there were gravitational waves even earlier, and that if they're actually detected, and they may be in the next few years, can give us some idea of words that you may have heard like inflation that we project happen even earlier in the universe. Of course, our goal is to go back and understand how the universe evolved from the very, very earliest times. But we're not quite ready to do that yet. So basically, we'll cover with gravitational waves the whole spectrum, which I showed in a different way earlier. I indicate here the different kinds of techniques that'll be used to do that, some of it being used now. And with that, I'll end. Thank you. Can I take questions? Can I take a couple questions?
We have time for one or two questions, not more. So, Yi Zhang, the president.
Barry, thank you very much for making such complicated experiment easy to understand for everyone. So I'm asked a question on behalf of all students. So to many of us, winning a Nobel Prize is just something we cannot, imaginable. So could you share with us what is your feeling when you received a telephone call from the Nobel Prize Committee?
I'll give the short version. First, so the question was, what does it feel like when you get the call that you got the Nobel Prize? In my case, I live in California. They announce the prize always at 12 noon in Stockholm, or as close to 12 noon as possible. That's 2 in the morning in California. So nominally I was asleep, but not really. So there was we had some indication that we might be contenders for a Nobel Prize for this. So I was kind of semi-prepared, went to sleep. There was no telephone call. Then I had set an alarm to get up to watch what happened. Started walking in the room to see who had won the Nobel Prize. And my cell phone started ringing. And that was the call. And it was immediately very convincing and very exciting to get that. I think you'll hear that from the next speaker as well. And the one after him, if he still remembers, he got his a long time ago. But it was very exciting, and it changes your life more than you can imagine to be made, well, look at the room here. So it's regarded as, it's one day a year when science is celebrated, is when the Nobel Prize is given, which is December 10th, the anniversary of Alfred Nobel. So in the sense of science and celebration of science, it's great. As giving individuals prizes for science, that's good for me as an individual, of course. But there's always a lot of other people that are involved, usually, in most discoveries. So it's a little bit of a two-edged sword. And in my case, I worked with many other people who did tremendous work on this. It could have never happened without them. But they only give the Nobel Prize to 3 people. So it's a mix.
Thank you. Thank you so much for this very clear and fascinating presentation, lecture. Very much. Really great. So we move now to the second lecture on neutrinos, key particles for understanding the smallest particles and the largest universe, by Professor Takaaki Kaita, University of Tokyo, Japan. Professor Takaaki Kaita was awarded the 2015 Nobel Prize in Physics, together with Arthur MacDonald, for the discovery of neutrino oscillations, which shows that neutrinos have mass. Takaaki Kaita.
Good evening. First of all, thank you very much for the kind introduction. And I feel it's really an honor to speak to you, young people. And well, before sitting down, I didn't, well, actually before coming here, I didn't realize that there are so many people in the second and third floor. It's really great to have these many people. Well, now I want to talk about neutrinos. And well, in this talk, I want to convince you that neutrinos are key particles for understanding the smallest particles and the largest universe. Okay, well. Okay, no. Okay, so this is the outline of this talk. First, I'd like to briefly introduce neutrinos. Then, I'd like to talk about neutrino problems about 50 years ago, or maybe slightly less. Then I want to move on to discovery of neutrino oscillations, discovery of solar neutrino oscillations, discovery of the third neutrino oscillations. And before finishing, I want to talk about the remaining questions and mysteries. Okay, what are neutrinos? Well, let me talk about the history about 100 years ago. In the early 20th century, physicists were puzzled with beta decays. Well, beta decay is a phenomena that a nucleus emits an electron. Then the nucleus changes to other nucleus. Well, if this is the true picture, the energy of the electron should be calculable, one value. Therefore, if one measures the energy of the electron, you should get one unique value. However, the measurement told us that the energy of the electron is not unique. This energy has a spectrum. So people were puzzled. Well, I don't know the real history, but I heard that some people even thought that in this subatomic scale, maybe the energy is not conserved. I don't know how seriously this was considered. But, well, certainly, conservation of energy is a very important concept. This red port, when nucleus emits an electron, in addition, there should be a neutral particle emitted. Well, so in this case, one can easily understand the continuous energy spectrum of electrons. So this was a proposal by Public. By the way, well, nowadays, if we have a great idea, we are asked to write papers. But here, about 100 years ago, he didn't write paper. He wrote a letter to people attending conference but he didn't attend conference. Instead, he went to a dance party and wrote a letter. So, well, maybe 100 years ago, people were more enjoying the physics. Anyway, well, certainly, if the idea, it's natural to think about the experiment to detect neutrinos. And well, in fact, well, it turns out it's not an easy experiment. Even in the early days, people realized that neutrinos can easily pass through various materials. But anyway, say, in 1956, which is about 25 years later from the Paris prediction, Frederick Reines and Cohen observed interactions of anti-electron neutrinos that were generated by a nuclear power plant. Then, in 1962, muon neutrinos were discovered by observing neutrinos produced by an accelerator. And here, I want to show you two photos. In the left, there are Linus and Cohen at the control room of the Savannah River experiment. And in this experiment, they observed neutrinos. And in this photo, these people received Nobel Prize in Physics in 1988. Surprisingly, the second neutrino observation discovery Nobel Prize earlier than the first neutrino discovery. Then finally, in 2000, how neutrinos were observed for the first. So we know that there are three neutrino types. Now, moving on, I want to summarize neutrinos. Fundamental particles, oh, thank you, I have. And you ask, cannot imagine what a neutrino is. Simplest answer is electrons, but we and if significant consequence, neutrinos can interact with matter very, very rarely. Therefore, it's possible for us to do neutrino experiment. And neutrinos have three types or three flavors, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to say that neutrinos have been assumed to have no mass. Okay, now this is the basic idea on neutrinos. But you still want to know, observe neutrinos. Well, of course, first see neutrinos themselves. Then, well, of course, in most cases, they simply pass through everything. But in their case, a neutrino has a nucleus. Then, in this case, a charged particle is typically emitted. Then, actually, we have various ways is charged particle. Let's assume nucleus, water nucleus. Then discharge it in the water. This particle, photons. These photons, and therefore, this way, we know that a charged particle propagates in the water, and that means a neutrino interaction occurred at that moment. So this way, we can observe neutrinos. Okay, now I'd like to move on to the neutrino problems. Well, solar neutrinos. The sun generated by nuclear fusion processes, and neutrinos are created by these processes. And therefore, the observation is very important to understand the energy mechanism of the sun. People try to understand the energy that of this one shown in the home stick. And this experiment observes in the first Ray Davis was the observed event rate by this detector was only about 1/3 of the prediction. Well, this observation event rate was continued since the end of 1960s. And therefore, people were puzzled, and this is called solar neutrino problem. Certainly, people were puzzled. People thought maybe be wrong, maybe the solar model be so accurate. People discussed various, but anyway, it's very important. Other experiment of solar neutrinos and confirm neutrinos are coming to the Earth. List the experiments, observation of solar neutrinos and for 1995. Anyway, these solar neutrino experiments, solar neutrinos, confirmed the solar. However, it was not for the deficit of solar neutrinos. Okay, this is the brief summary of the solar neutrino problem. Now, I want to talk about the other problem. I want to talk about the atmospheric neutrinos. Well, there are cosmic rays. These are particles from the universe to the Earth, and these high energy particles, protons, sometimes helium nuclei, or in some cases, even these particles come to the Earth. If these particles come to the atmosphere, here, particles interact with the atmosphere, produce particles, and these and neutrinos are created at the time. First of all, this kind of expectation exists. And in fact, atmospheric neutrinos last time by detector extremely deep underground in the left, and one and experiment successfully observed atmospheric neutrinos. Then I would say atmospheric neutrinos were actually not the main topic of physics for some time. But in the 1970s, there was a new theory called grand unified theories. And these predicted that protons should decay lifetime of about 10 to 30 years. Of course, 10 to 30 years time. But if we observe this proton for a year to observe a proton decay, several proton decay experiments began in the 1980s, and here I did proton decay experiments in the 80s. These proton decay experiments observed many because atoms at the background to the proton decay searches to understand the atom's ground. The Kamiokande and IMB experiment found a significant deficit of atmospheric neutrinos, muon neutrinos. Well, so the data were interesting, but again, at that time, we didn't know what was the cause of the deficit of muon neutrinos. Well, certainly, we know why were observed less than expected. Muon neutrinos were observed less than expected. But people were thinking this was just maybe. Maybe the problems are related to the neutrino oscillations. Well, let me tell you. If a mass, neutrinos change their type to the other. For in this case, a neutrino is created to propagate to the right. But then the neutrino type come back to muon neutrino, then tau neutrino, and so on. So this is neutrino oscillations. And in fact, neutrino oscillations were already predicted more than 50 years ago by these people, Maki, Nakagawa, Sakata, Pontecorvo. Okay, now I would like to move on to the discussion of oscillations. the main experiment related to the discovery of neutrino oscillation is on the experiment. It is very, very large underground. 40 meters in diameter and 40 meters, and it contains of extremely clean. And I Kamiokande detector. And people are, and you see the wall, and this wall is the detector wall. So you can understand how big the detector is. By the way, this is an international collaboration. So at present, scientists from 11 countries are coming to this detector and working together. Now, I mentioned that neutrino deficit was observed in Kamiokande and the IMBX. But at that time, know what happened. But as I neutrino oscillation from the actually from the explanation, it is possible for other reasons. It's very important where the it is due to neutrino oscillations, other. So, thought this by cautions in the atmosphere. That means these neutrinos are created everywhere in the atmosphere of the Earth. Therefore, some of the neutrinos are created above the super Kamiokande detector. And these neutrinos come to the detector after traveling typically 10 to 20 kilometers. Well, maybe 10 or 20 kilometers could be short. Therefore, neutrinos may have no time to oscillate. On the other hand, of course, neutrinos in the other side of the Earth. These neutrinos must have a very long distance before reaching the Kamiokande detector. Typically, have to travel about 10,000. Then, very long distance, therefore, thought we see up versus down going in front. Indeed, from Super Kamiokande, actually a very old data conference in and well, in this plot, there are two panels. Upper one is for electron neutrinos and the lower one is for muon neutrinos. And please see the lower one. And the horizontal axis is the zenith angle, or more simplified word, cosine theta 1 means downgoing neutrinos. They travel typically 10 to 20 kilometers. 1 means upward-going neutrinos. They traveled more than 10,000. And the black dots and the hatched histogram shows the expected without oscillations. Then you can easily find neutrinos, the data, and the read rather well. On the other hand, look at the upward-going neutrinos. The observation was only observation. Distance. Therefore, when the detector remain as mu, I think we were able to convince the world community of neutrino physicists that neutrinos oscillate. Well, we were excited, but, well, of course, as a physicist, we were excited, but, well, we were very fortunate that there was President Clinton's talk at the MIT CH commencement. And talk, he made discovery of neutrino oscillations. Well, in his about 30 minutes talk, the middle, he mentioned this way. Japan physicist announced that tiny neutrinos have mass. Not mean much to most Americans, but most fundamental theories. Subatomic particles, and indeed how it is. Then the issue is that these conditions that are not limited, they affect the whole of society. Our very relations with others and our place in time. So I think we were really honored to hear this kind of words from the US president on the next day of our discovery announcement. Well, okay, now, from now on, I want to move on to the second discovery of solar neutrino. As I said, solar neutrino problem in the 20th. Let me mention about the initial how to solve the solar neutrino. As I mentioned, people were puzzled neutrino data. Some people not be accurate. Maybe neutrino oscillate. No conclusion in the tweet. Then there was a great idea. We measured the electron neutrino flux. So it means electron plus mu. And if the electron neutrino there should exist mu neutrino plus tau neutrino flux from the sun. But the sun can only generate electron neutrinos. So if we observe this effect, that is the evidence for neutrino oscillations. And for this purpose, solar neutrino experiment with heavy water was, and in fact, this was a proposal. And based on this idea, experiment was constructed. This is the detector, and central region pounds of heavy water is used. You can see a full snow detector under construction, a very big vessel. By using neutrino interaction target, solar neutrinos. And indeed, snow neutrino flux only, the observed flux was about 1/3 of the expectation. However, if the snow experiment observed the total neutrino flux, electron neutrino plus mu neutrino plus tau neutrino flux, the observation was just consistent with the expectation, solar model expectation. And that means about 2/3 of the neutrinos from the sun should be mu neutrino or was the clear data telling that indeed the deficit was due to neutrino oscillation. I'd like to quickly move on to the discovery of the patient. There are 3 neutrino types, actually 3 types of neutrino oscillations theoretically known. After the discovery and the second neutrino oscillation, the communities discover the relation. Well, in fact, experiments are the neutrino. The upper ones use neutrino beam produced by accelerators. And the lower ones observed neutrinos by nuclear power plant. And remarkably, these experiments around 2011 and 2012 observed the effect of oscillations, as neutrino oscillations. So, more than 10 years ago, we basically understood the 3 flavor neutrinos. So, we basically understand the structure of the neutrinos. That is great. Now, in fact, I want to the whole neutrino connected with the neutrino, and here is the neutrino experiment to the understanding of the. So, I want to go into detail. That there are many experiments of neutrino significant suggest that we are really excited Okay, now, from now on, I want to mention about the remaining questions and mysteries. Oh, by the way, so far, I simply said, we are excited. But you may wonder, why we are so excited. Certainly, like electrons, quarks, they have mass. In a sense, it's natural mass. But excited. Let me tell you. Here, I show charged leptons, electrons, muons, and also that groups are shown by red color. Also, the mass of quark colors we have been working hard. Neutrino community has been working hard to understand the neutrino mass. And indeed, I think we understand the neutrino mass rather well now. So let me plot the neutrino mass. They are about here. So, well, first of all, you find that the neutrino mass are plotted in a rather separated place in this plot. And please be careful. Horizontal axis, where it is 100. So it's separated by 2 units, that is 10, and 3 units, that is 1 million. So then find that the neutrino approximately, or maybe more than 10 billion corresponding mass of quarks and charged 10 times smaller, or 10 orders than the other particles' mass. So, we believe the key to better understand even the universe. And why mass are so small, our understanding on elementary particles should be improved, much improved. But we think that in addition, maybe the neutrino mass could be related to the understanding of the universe. Let me tell you why. Well, this is a photo of the far universe. There are many galaxies. But these galaxies are by matter. Antimatter galaxy. But actually, we don't understand why the present universe only. Well, about years ago, the universe was, and the was incredibly hot. Incredibly hot universe. Always and the antiparticles are, that means with equal number and with the universe particles, then the particles and antiparticles meet and annihilate, disappear. So you can easily imagine there should be no matter particle, no antimatter particle at present, but which is not true. So what happened? Well, how understand what happened during Big Bang? There were, say, 1 billion plus 1 particles. On the other hand, the particles were 1 billion. Well, 1 plus 1 and 1 billion is all. Then, with the union, matter particle and annihilate disappeared. At present, particle remaining. Understand. Of course, well, 1 is almost equal to 3. Therefore, why there was that maybe neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So maybe neutrinos are the key to really understand the universe. So, and since this is an extra question, people are thinking that we should experiment this idea. Yes, there are actually projects going on. And, well, in fact, in these we'd like to observe if neutrinos and those of antineutrinos are different. Maybe confused, but observe. But in order to see the difference between neutrinos and antineutrinos, that the present powerful enough. Therefore, going into details, but I would like to simply say that these experiments are extremely large, extremely complicated, and these are under construction, and we hope that we see the results from these experiments in the 2030s. Now, before finishing, I'd like to mention one more thing. The question is, do we really know mass? There are 3 neutrino mass. And usually, we assume that the mass, which is shown by black circle, the heaviest. But we'd like to ask if this assumption actually in the history of the study, we had many it could be possible that our so maybe here is the lightest. The present, if the third neutrino mass is really the heaviest. And for this, again, we need the next generation neutrino oscillation experiments. And I'd like to briefly tell you what will happen rather soon. Well, there's an experiment called Juno. This is the photo of the Juno experiment. And well, by looking at this photo, you may have no idea how big that, but over there, you see in fact, this is about diameter, so big. This world's largest 20,000 located near, well, in China. Anyway, on the true Newton, there should be small in oscillation. I would like to observe small oscillation pattern just through and the good scintillator next year. So the experiment will start soon, and we hope to see the result from this experiment rather soon. And finally, before finishing this talk, I want to mention one thing. This is the map of the Earth, and from the talk, I mentioned many neutrino experiments. Now, I want to location of these neutrino experiments, and they are here. So, well, in many places in the Earth, experiments are going on or carried out. Experiment is carried out at the south, or well, in many places. I want to say that many of them in operation. We are global to understand the neutrino rise in understanding neutrinos are in understanding the smallest particles and the largest universe. And studies of neutrinos or studies of physics in general is a global effort. And I hope I convinced you that physics is great, and I hope become physicist. Very much.
Thank you, Takaaki, for telling us the history, the saga of neutrinos. It is a global effort, including China, with Juno. This is typically like with physics, to contribute to collaboration, global collaboration. there is room for one or
generation, the first generation. Now you also mentioned electron, and mu nutrition. Are those two concepts related? Here?
I got.
Sorry, you mentioned the first generation neutrino, second generation neutrino, third generation neutrino. You also mentioned that there is an electron and a tau and a mu neutrino. So explain the meaning of the relation between two.
Yeah, thank you very much for this question. Actually, intentionally avoiding to tell the detail. Well, for example, I say the neutrino. I'm really talking about the neutrino mass state. The lightest, second lightest, and the third lightest. This does not mean the electron neutrino. Actually, they know the relation between the mass state and electron neutrino, mu neutrino, tau neutrino. Complex mixture of that was too simply try to avoid.
question, yes.
Short one. Suggesting dark matter con neutrino if they how much
Thank you.
Contribute.
Yeah. Thank you. Well, in fact, nowadays, we know the mass of the heaviest neutrinos. And in fact, the mass of the heaviest neutrino is simply too small to be a significant part of the dark matter. So find out what are the real dark.
Thank you very much. We can upload loudly Takahika's wonderful lecture. So the third lecture will be on Zoom, will be virtual, will be online. So we can get into a relationship with Professor Samuel Ting. Samuel Ting is at CERN. You hear me? Yes, here is comme si
Yes, I can hear you.
Perfect. Thank you very much. So I will introduce your lecture. So the title of your lecture is 50 years since the innovation in physics and unearthing the secrets of the cosmos. The speaker, as I said, is Professor Samuel Ting from Massachusetts Institute of Technology, MIT, USA. Professor Samuel Ting was awarded the 1976 Nobel Prize in Physics for discovering a new subatomic particle, the J particle, now usually called particle, the first of a new nuclear massive, long-lived mesons. The floor is yours.
Okay, thank you. Good Professor Michel Spiro, member of the IUPAP, Professor Zhang Jie, member of CPS. Enough for me to lecture to you. It's really, I'm not in Hainan. In this time, was 50 years ago, New York Times, the new and surprising type of atomic particle found. Let me share with you how this experiment is done. It's a consequence of a series of experiments. The first experiment is measuring the size of the electron. Modern electromagnetic theory, quantum electrodynamics, QED, require the electrons have a radius. This was done by Feynman Malaga in 1948. Theory agreed well with the experiment. Here, a 6 billion electron volt Cambridge electron accelerator provided a more sensitive measure of the electron. This experiment was carried out by Harvard, done by world's leading for many years to develop the Cambridge electron accelerator, energy electron accelerator. As a circumference meters is joined to the machine. It generates radiation of 6 billion. When you go to the atom, from the recoil photon, you have a virtual electron. From uncertainty principle, you can measure large momentum transfer, therefore determine the radius of the electron. This is the measurement in 1964 by the Harvard group. Their measurement compared with quantum electrodynamics, it shows they are deviate from quantum dynamics at a distance between 13 to 10 to the minus 14. So the data has the size of 10 to the minus to 10 to the minus 14 centimeters. Most importantly, experiment verified by a group touch upon the foundations of modern to perform the experiment. At that time, I'm thinking about you, so I knew also the US. I decided to move to the new electron Germany experiment to remeasure the size of the electron. So from 65 to 72, I did a set of experiments at Beijing. At that time, this is the size of the electron accelerator, and this is the detector. It is the development of this type of detector leading to the discovery of J particle. And this detector at that time, the two young persons, this who was for many years the vice president in charge in Princeton University. So I have 10 to the gamma rays per second on a target. First thing will happen, you produce enormous amounts of gamma rays and pi. DC magnetic spectrometer, electron positron. A set of position definitely, but velocity you need is non-digit target. And therefore, the neutrons or gamma pi. I can define by the age. The two Cherenkov counters are separated by a magnet in each arm, so that the background E plus E minus produced from interaction in the first counter are swept away by the second by the magnet and do not into the second counter. So these two measurements of velocity identify the electron in the trajectory in the measure the momentum use a total to measure the velocity and to project large background you require equal to energy at high energy. In 66, our group completed experimentation. The electron indeed has a radius less than a centimeter. So this is our method theory, sync from electrodynamics. Results in 66 are now known as Wolfgang Panofsky, and I maintained close contact with them for many years. So this was the first paper published in January 1967, and so this is the control room, and there's me, the two graduate students, and the technician. And so this was the computer, which is now probably an iPhone. And this is a celebration for the success of the experiment. Common result on photons. When you measure a photon inside the nucleus, the electron-positron pair, dynamics, and omega and phi. This will break down the dynamics, but change to a massive photon to E plus E minus. So my second photons and heavy fast zero. You have the 3-pair resonance. Phi is the 2K resonance. Their mass is below 1,000 MeV. But more important, photon and heavy photon have same quantum number. J equal to 1, C equal to -1, P equal to -1. Therefore, you can imagine a photon interact with the nucleus, can be visualized as photon row interact with the nucleus, go to a phi. And so you have the curve equal to the rho part, omega part, and phi part. The question then is, what is the relationship between photons? And so I move to again to modify with major improvement in quantum resolution and partition. The first thing of coherent interference decays. Rho pi omega is a not interfere in the pi 2 pi and others. But omega and another photon go to the photon, go to E plus, E minus. So rho omega should interfere not in the pi state, but in the E plus minus final state. And this has been looked for and never found before. And that is because the branching ratio of rho to E plus E minus compared to rho to pi is 10 to the minus 4. A clean experiment, you need order of 10 to the 7 to 10 to the 8. And this is the first observation of coherence between rho to the and omega to the electron pair. For mass of E plus E minus does not rho to E plus E minus, but having enhanced rho decay and omega decay. We also measure pair with this measurement. Check indeed one rho, the branching ratio rho is equal to the branch of and branching ratio of pi. From that time, I began to what was observation isotopic spin 1. Omega has isotopic spin 0. So they do not interfere in the pi mode. But the omega can go to a photon, photon go to rho, rho goes to 2 pi. So in the pi mode, there must be a decay. And this was started by Nobel Prize winners Glashow, Weinstein, Feinberg, Gordon, Sachs, winner, Steinberger, and nobody has done. So we observe the 2 pi resonance. Our photon again produce pi mode. The PVA from rho to 2 has a rho to 2 pi, omega to 2 pi. So this is on the discovery of the J part. We learned that photon and heavy percent, they do transform. The question is, why should there be only type of mass below 1 G? Higher mass will move to higher. Was paid for by the National Laboratory in 1970. So we stated clearly, the best way to search for vector meson is through production experiment. A proton goes to vector meson, decay to E plus E minus pair. The reasons are vector meson produced by a strong interaction in this case, and therefore you have a high production rate. One can use high-intensity, high-duty cycle extracted beam, namely the sensitive view accelerator beam out of the accelerator view. Third, the E enhancement quantum number to 1 minus, enabling us to avoid measurement of angular or decay products. I stated, contrary to popular belief, the E protein is not the best place to measure. The E plus E minus storage a systematic search require continuous monitor to colliding beam. Almost infinite machine time. To perform detailed parameter once they are found. I have an experiment. It's a different. Order is 10 to the 12 protons per second on a 10% correlations with the brilliant target. And so the multiplicity of this energy is 10, and therefore you have 10 to the 12 particles. Out of the 10 to the 12 particles produced, the E plus E minus pair is estimated to be less than 1 in 100 million. If you want a 1% experiment, you must have a rejection between signal to background 10 to the 10. This means the raining season over high cohort per second, you need to find not popular the physics community. This believe search photons are not the most that about quark model. I think that 3 said that a difficult experiment could be carried out successfully. So the proposal was rejected by most of the leading laboratories. It was finally accepted by Brooklyn National Laboratory. So this is the top view of the detector. This is the side view. The top view, so the beam is 10 to the 12 per second. On a target, you have M0, M2 of dipole magnet, CE, actually measure the velocity, A0, C are proportional chambers measure the core. Small a, small b, triggering counters, S is the shower counter. Looking from the top, there's no bending. You may this occur in the side view, and you may momentum and follow the design daisy. And we have on the side a circle very close to the target. And this measure provide a electron beam to calibrate the detection. When you have 10 to the 12 particles per second on a target, you produce 10 to the 12 particles. How do you protect yourself? And so we use 10,000 tons of concrete, 5 tons of uranium, 100 tons of lead, and 5 tons of soap. Soap is used to slow neutrons. So this is the area view when the roof is open. So there are many procedures thought well do because really it's nearly environment. The first thing we did is to mark it into many thin small pieces. Have good resolution. A real E plus 1 point in the top. We will have a E plus in target. And you can see of events show the location of the target. To understand magnet with a 3-hole proof, over 10 to the is smaller. Defines the charged particle to an angle so the detector are not exposed to the target, and therefore neutrons and gamma rays are swept away from the detector. More difficult thing is the rejection of 10 to the 10. The first thing is a pion going to the Cherenkov counter could not put the atomic electron, so a pion becomes an electron. Then you will misidentify the particle. You use the radiator with the lowest number of that is hydrogen. So we use hydrogen. And then the Cherenkov in the magnet with a diameter of 1 meter. Other Cherenkov counter behind the second. The two counter magnet, minute number in the first counter are swept out into this. So this you can look. First of all, you must have no material in the beam, so they're made out of 125 micron mylar on both ends. You have a large mirror, 1 meter in diameter, 3 millimeters thick. This was designed by my two French colleagues, and Jean-Jacques Aubert. The mirror at the precision optical shop at CERN. This shows the spherical mirror plot. And the special photometer were made to identify 1 photon, 2 peaks. Then how the electron beam to calibrate your detector? You use the fact you produce many particles through the main channel. The electron from pi 0 decay magnet, you bend the electron by this Cherenkov counter, go into the output spectrometer of E minus Ca as this Cherenkov counter as E plus. Therefore, you produce the electron beam to calibrate your detector. This Cherenkov counters, you want to make sure it's 100% efficient, and so you have 200 combination measurement and shows they're all close to 100%. Nobel made major contributions of the experiment. He later on became professor and director general of IUPAP, close associate of Bureau. The detector was designed by student, the late Professor Ulrich Becker. There are 20 make up through these detectors. In fact, each chamber lines a plane part. The 60-degree triangle of the property 1 plus x3 is equal to b. This and this later on was exhibited in Smithsonian Institute in Washington. In order for the detector to work, it has a position accuracy of 1 millimeter. You have 10,000 wires. Because you have such a high rate, you have many tracks going to the detector, and so the detector wires are all arranged 60 degrees apart. The first chamber for calibration. So for each 3 wires to be constant. They operate all at rather low voltage, so to radiation area. This is the tracker together with the chambers of time. In the early summer, we took some data in high GeV and show very few. By the end of August, we tuned the magnet of 2.5 to 4. We begin to see a sharp. All this we can publish. So, in the group with regard to experimental checks on our data and on the data analysis. I make a few examples to share with you and still apply to my current experiment today. The first, instrumentation check. To make sure that we observe peak is a real effect, not due to instrumentation bias or readout errors of the computer. Another set of data, a lower momentum curve. This has the effect of moving different part of the detector. The fact that the peak 0.1 GeV shows that a real particle was area is normal. The white area is 10%. November, 3 paper, November 12, of heavy particle J, the psi particle published in some resonance of E plus. A few days later, a particle was identified. J particle. Group, and this is Professor Ming Chen, who did a lot of work on analysis. This is Jean-Jacques Aubert, who did the joint cup count. The unique property of J particle are its lifetime is 10,000 times longer than other particles. After the J particle discovered, both first from Daisy, then from SLAC, and you see particle. The translation is very similar to the E plus image. The lifetime is 10 longer, means it's southern family in the remote region of Earth where people to live instead of 100 years old. So something new, something unexpected. Spectrum is very similar to also implies new. It is from this moment on gradually developed in 3 quarters. The J particle confirmed the existence of charm and European glass shell, particularly put in glass shell Minneapolis, 19. After I received the Nobel Prize notice on October 1876, I received a letter from Richard Feynman who basically says, congratulations, but why do they give prize to people who discover things I don't expect and don't understand? Most important, please do not let the prize go to your head. For this reason, I never sign anything name on things I don't understand. Her and I attended the Nobel Prize ceremony December 10th in 76. This is Richard's Elizabeth, and this is my 2 daughters. Nobel Prize. Last year was 2019 Institute done a systematic study right after discovered, and they were Italy, in Beijing, PC2, and Caesar in Cornell, Webb in Moscow. And this slides are provided to me by current leader of the Institute of High Physics, Yifan Wang. And so the JSI continues for 40 years in Beijing, the electron positron accelerator. And in the original accelerator, they have 9 billion events. Construction is 1988, and 88 to 1995, data taken. And they have an upgrade of the accelerator, and then the second upgrade, the first upgrade factor took more events, and upgrade the accelerator, the event in the new leader I just mentioned. You can see from here spectroscopy. 58 million, you see 1835. You're 20. Today, with 10 billion, you indeed see many more structures. In total, 30 new hadrons discovered in battery for charm meson production and decays. So this is a really extraordinary achievement. Now let me share with you electrons at high energies, namely at the 46 billion electron in Hamburg. And let me touch upon international collaboration physics, and this is the first time Chinese outside China after the couple with us. The creation of the March experiment. After the Cultural Revolution in August, the Chairman shall scientists each year. So current Chinese scientists are joining my contribution were Professor Kachi had no experiment on Chinese work in the market firms to some electrodynamics, namely continue to look the size of the electrons and the electrowake theory. To measure electrowake theory, you measure E plus E minus, mu plus mu minus angular resolution. Since the effect is small, to reduce the systematic error, the detector, which is with 1,000 times, can be rotated and in 5, and therefore to resolve the systematic error. This is all and was published in Physics Today. Interference confirmed. What was E plus E minus to mu plus mu minus? D alone, you have the yellow. We measure is the green line, the data point, and that is unexpected discovery in Germany. E plus you produce for gluon jet, which is the third. The gluon jet, a charged particle, a neutral particle. The three jets, if you spread them apart, there are many possible explanations. Phase space and large momentum transfer. It's only by measuring the total energy, charge and neutral, statistically with the QCD. And this is an article in 1979, and there, for the first time in the history of the national project on nuclear particles, no contribution come from China. 20 school scientists working. Then let me share with you a even higher energy, which lasted for 20 years, with 100 GB. This is a large international collaboration in the United States, China, India, and so forth. Also, they contribute to a very precise 300-ton, 100,000 channel colorimeter. A unique technical development is BGO crystal to provide accurate measurement of photons and electrons. In '83, when we started the experiment, the working of BGO was 4 kilograms, and I need 12 tons. And of the technical development was the production of BGO crystal in 3 years. By Shanghai Institute, together with the Lab Energy and the Moscow Institute of Theoretical Physics. This is one of the 12-ton, 12,000 geocrystals are now in Wisconsin. The many, there's 3 that first, it does change within one company concerned alpha, it decreases with the energy. is a photon alpha. Also, extended measurement of number of neutrinos. By measuring positron, electron, go to neutrino, antineutrino, photon. Namely, no charged particle coming out. By measuring the photon, and you see, we determine the number of photons in the universe. Now let me share with you our latest experiment on electron positron at the highest energy, namely the AMS experiment, International Space Station. Charged mass, and they are absorbed by 100 kilometers atmosphere, which is 10 meters of water. Properties such as the sign of the charge, the value of the momentum of charged cosmic ray, cut on the ground. On the ground, you can study the energy in the direction. To measure cosmic ray charge and momentum require in space. This is a very construction in Europe and Asia. Tests European Space Agency, and there's various countries participate. Sent to space 2011, 26. We are adding a major upgrade by adding 4 square meters of silicon fiber to increase acceptance to 300%. So let me share with you the latest cosmic electron positron antiproton backbone. They can come from only 3 sources. One is ordinary cosmic ray collision with interstellar media. So you have cosmic ray collision, positron electron. Yeah, and this will always occur. But the dark matter is a particle form you have. And then you can also produce positron. A pulsar, which is a rotating neutron star, high magnetic field. A photon intergalactic field can produce positron. Pulsar cannot produce antiproton because of heavy. Order period. Because nobody, this is the measured from very low energy EV, and this is measured flux based on 4 ends. The low energy partition. The question is the high problem or dark matter, because there are only 3 possibilities. But if you look more carefully, the spectrum can be fit empirically by a collision part, like for the low energy, and plus pulsar and dark matter part. But the spectrum must have a cutoff energy, exponential year over year. And this one exists in the 4 sigma lab, 4.8 sigma lab. It's a very, very strange phenomenon. Why the spectrum goes down at such high energy? So if we compare what I expected to this is the current data. The current low energy part from cosmic, high energy part from dark matter 5 TeV. And the agreement is called because the so by to those will greatly reduce the error. Did indeed agree the causation model also will first, the electron from collision is negligible. The electron spectrum based on 6.2 10 to the 7 event from very low energy to multi-TeV can be empirically expressed by a power law A plus a power law B and plus a positron term from the positron source. And this at this moment 98 confidence level by 2030 and 0.99%. And new sources like will produce equal amount of electrons. It's antiprotons and positons. This is a measurement of antiproton, 2 million events. We found CGV, antiproton, it's exactly the same. This is based on 1. By 2035, more refined agreement behavior of positron and GeV exclude the antiproton. To understand this, we also study all the other cosmic rays. Cosmic ray has two kinds. One is the primary cosmic ray, proton, helium, and so forth. They are produced during the lifetime of star and accelerated by supernova explosion and propagate through interstellar before reaching MS. So measurement of primary are fundamental to the understanding of acceleration propagation process of galaxies. With the great surprise, primary cosmos have two classes. Light element, oxygen, and the heavy element, silicon, each have their own with independence. For very low energy, rigidity is momentum divided into two. And then let me mention lithium beryllium boron produced by collision of interstellar media. Cosmic rays are important station of cosmic rays. Secondary cosmic rays have two classes of rigidity dependence. Lithium beryllium boron is one class, and fluorine is a different class, from 30 GeV to 3000 GeV. As function of Z, light element, therefore, helium, carbon, oxygen have one rigidity dependence, lithium, beryllium, boron have another rigidity dependence. Heavy element from neon, magnesium, silicon has one rigidity dependence and another rigidity dependence. This measurement can be explained with current derivation. Let me now study the abundance element in the solar system. Element in the solar system measured from analysis and meteorites. No, then you can look compared to silicon. In neon, silicon ion is much more. So lithium, beryllium, boron at the lowest rate. Secondary oxygen are primary cause. The further surprise to account that boron's pure secondary. The B over C ratio has been used in hundreds of models to describe cosmic ray propagation. But what we found with accurate measurement, the spectrum of carbon is a composition of primary, which is equal to 0.83 times oxygen's pure primary, and plus, which is 0.7 times boron. They agree perfectly over the range. So carbon, therefore, the question is now what to do with of theory, use them as a. But furthermore, found even then you have distinctly component. For example, sulfur is by primary cosmic ray. Nitrogen, sodium alone become much more dominant. Now we can look for all. Most of them are combination primary and secondary, with very few are pure primary. So there are total 28 elements can be measured. The rest, lifetime is short, you cannot see it. Out of 28, we have measured 21. And the 21 element basically has 4 types of rigidity dependence. Primary has 2 kinds. Now let me information on antimatter. The big universe requires matter and antimatter equally abundant at the very hot beginning. So where is the antimatter universe? Antimatter has never been found. Heavy has never been found. Anti-deuterium candidate from 100 million photons. This is in the bin. And this is the chunk of. And another this mass plus 5, the mass is 1. That's the opposite of deuterium. And this is an anti-helium 4 event. Analysis of this event showed this event has charge -2 plus minus 0.05. The mass is 3.81 plus minus 0.29, the opposite of helium 4. So space is the ultimate laboratory. Space was much higher than accelerators. So we are a first small step in the mystery of the cosmos. Result contradict current cosmic and require the development of new cosmos. So thank you. Have questions?
Thank you very much, Professor Samuel Ting. View of breakthrough and conducted professional life. Many of them in his physicists. Questions? Yes, do you have a question?
I don't hear anything.
Professor Dean, can you hear me clearly?
Yeah.
Okay, thank you. And in fact, I know a little about dark matter. So I want to know, can you tell me more properties of dark matter, the antimatter and the shape of dark matter and antimatter? Can you express more? Thank you very much.
No, I cannot more, because dark matter has not been, we have candidates, we have not concretely, and so I don't know, antimatter and dark matter are not related.
Thank you.
There is two independent mysteries and the existence to Professor Ting. You started to be a little bit tired, so we had yes, there is one question.
Thank you, Professor Ting. I'm very curious. You say you have been working with many Chinese scientists in the very beginning after Cultural Revolution. So I'm very curious about what are their challenges and difficulties for the first student or scientist working with you.
No. They have, I have suggested to the government choose scientists think independently. They did really a very good job. Choose scientists to work with. Now, after 40 to 50 years, we have many Chinese work. I suspect close to 1,000. Most of them are really quite good. Like my collaborators they're exceptionally good, and they are good, and they are average, and few below average. It's almost all the same. You cannot say Chinese is better than the other on the average, or worse than the other.
Thank you.
So thank you very much again, Professor Ting. This was really illuminating for all of us. Thank you.
Bye-bye.
So, end of this special evening session, IUPAP and CPS. I remember this evening session for long, and that it will be a young audience in this room. Have a nice evening. The session is. People for the people to stay here.